Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Welcome back to Whimsical Wavelengths, where I'm going to pivot back to my wheelhouse, volcanoes. Yeah, that's right, it's my turn, honestly. Though, with a podcast, it can always be my turn, but that would just be boring for me. I'd rather learn about tyrannosaurs, NASA traditions, and novae, and about the evolution of aging. In fact, if you're new to Whimsical Wavelengths, I suggest going through the back catalog, especially the ones where I have guests. Today, though, I'm picking my favorite paper that I wrote. The Origin of Mauna Loa's Ninole Hills. Evidence of Rift Zone Reorganization. And it was published in Geophysical Research Letters in 2015. 2015. Yeah, it's been nearly 10 years. Well then, perhaps it's time for a 10-year anniversary tour? Some say grad school was the years of their lives. Perhaps I'm still trying to graduate from those memories? As for a Mauna Loa joke, I had one. I swear I did. But I'm worried it might erupt into laughter. Well, it's time to do a little bit of background first, and then circle back to who and what the Ninole Hills are, and then into the paper and how the story came together. So, Mauna Loa Volcano. It's located on the Big Island of Hawaii, part of the Hawaiian archipelago. The island chain is a result of the relatively fixed hotspot underneath the Pacific Ocean. The hotspot track can be traced to the northwest all the way to the subduction zone at Kamchatka on the Pacific coast of Russia, pretty much 5,000 kilometers away. Plate tectonics, I mean, it's amazing and just great. And also, sorry for those who already have a strong understanding of our dynamic Earth. But again, this pod is for everyone, and so I'm going to be covering a lot of introductory material. So the upper portion of the Earth that behaves like a rock, i.e. it breaks and we get earthquakes, it's called the lithosphere. Separate regions move together and distinctly from other areas, which we call plates. The movement is slow, and per year it moves about the amount your fingernails grow. There are two basic types of lithosphere: continental and oceanic. As the name implies, oceanic lithosphere normally represents the ocean basin, so the ocean floor. And continental lithosphere is the land most of us live on. There are caveats and nuance here, but we're here for the Mauna Loa and the Ninole Hills. But I still feel like I should explain how we get and what the difference between oceanic and continental lithosphere is. And to begin this explanation, I need to tap into something everyone who's listening has some experience with, probably anyway. Water. An inner tube or pool floaty sits on top of the water with no human weight applied to it. Add a person and it sits lower in the water. That is all you need to understand the basics of isostasy, the process of the Earth's crust adjusting to changes in weight. So the ocean lithosphere is denser than continental. If there was no oceans, it would be topographically lower, as it is denser and sinks into the other layers of the Earth that don't behave as a solid in the same way. I once told a joke about density to a bunch of first years, but they didn't get it. I guess they were too solid to absorb it. One more thing before going back to Hawaii and Mauna Loa and hotspots. Why do the plates move? Well, we can separate that into one, convection in the mantle. So that's heat driven, and we see this all the time when you boil a pot of water. Hot air rises, that kind of thing. Two, ridge push, which is gravitational force at spreading ridges. And three, slab pull. So obviously I've already explained convection is by far the easiest to explain. Heat causes changes in density. Hot air rises, and I'm definitely full of hot air. It's the reason Whimsical Wavelengths is rising to the top. Ridge push. This is where two plates move apart. New crust or lithosphere is created. It's hot and it's thin. And therefore, based on the ideas of isostasy that we just explained, it doesn't have much weight to try to push down into the Earth. So it is a topographic high. So it's a high point gravitationally in comparison to the rest of the lithospheric plate that it's moving with. So it's pushing the rest of the plate down and forward. Slab pole is the one we haven't talked about yet. As oceanic lithosphere gets old and cools, it eventually incorporates water into its lithosphere. Both the processes, the cooling and incorporating water, causes the oceanic lithosphere to become denser than the mantle below it eventually. And at a subduction zone, it will sink into the Earth, dragging the rest of the plate behind with it. Okay, that explains why the plates in plate tectonics move, at least the basics. Zooming back down to the Hawaiian hotspot. Hotspots are similar to what their name suggests. The best model we have for hotspots is an upwelling of material from deep in the Earth that stays approximately stationary while the lithosphere moves on top. Even though this material is moving upwards, it isn't correct to say that it is a fluid. It isn't magma. Sure, over long time scales, it flows or moves, but it still has shear strength. Seismic waves, S waves or shear waves, pass through it as if it is a solid. It's really important, and this is the reason why we know that the outer core is liquid, is because of shear strength. Liquids do not have shear strength, so seismic S waves or shear waves cannot pass through them. And if something is partially liquid, so it has a reduced shear strength, we can actually measure this. So we know that this material is solid. The vast majority of the mantle is solid. However, as this material moves up, the pressure is starting to be reduced, and it's hot, and the melting point is crossed, and magma can be generated. Once there's enough magma, it can rise up through the crust to form volcanoes, i.e., hotspot volcanism. And as the plate continues to move, you get a line of volcanoes, much like the Hawaiian archipelago. A nice line that you can trace all the way back due to plate tectonics. Okay, there's the background, to set the scene, if you will. Now zoom in a bit further to Mauna Loa, the largest volcano on Earth. Mauna Loa has erupted 16 times since 1900. There was also a time in its geological history where it was erupting much more frequently, much like Kilauea is today. Remember, as I've already said, the lithosphere moves, but the hotspot stays approximately stationary, meaning if the heat and supply stay constant, there'll be new volcanoes born and old ones will become extinct as the plate moves. Kilauea is younger than Mauna Loa, but it isn't the youngest volcano in the Hawaiian archipelago. That title goes to Loihi, which is just off the coast of Kilauea volcano. And even though Mauna Loa erupts less than Kilauea, it still erupts fairly often. 16 times since 1900. But to really appreciate this process, we need to look at its lava flows. In the past 4,000 years alone, lava has repaved 90% of Mauna Loa's surface. And Mauna Loa is flippin' huge. At a whopping 5,270 approximately square kilometers of surface area. We're talking about, of that 5,270 square kilometers, 4,743 square kilometers has been covered by lava in the last 4,000 years. 90% of its surface. And some of those areas have been repaved multiple times. Yeah, it's a dynamic place. Yeah, the surface of Mauna Loa is very young geologically. And all that repaving obscures its internal structures and earlier evolution. You can't see because it's buried. That's the case with all geology, of course. Layer upon layer is laid down, and it's hard to access the stuff below. We just had an amazing discussion about tyrannosaurs and being able to get dinosaur fossils. And we can do so in Drumheller because we have access to the geology that's there. At a volcano like Mauna Loa, we don't have access to the stuff that's old. It's all been repaved and buried under new eruptive products, more lava. Therefore, to open a window into Mauna Loa's history and internal structure, we need to use specialized techniques to image concealed structures and intrusions in magma chambers and the like. Therefore, we need to use something like geophysics. In this case, in this particular study, I used gravity. I took a box with a well-calibrated and delicate quartz spring around to different areas of Mauna Loa on the slopes to measure the amount of gravitational force pointing down to the center of the Earth. By taking measurements over a wide area, I mapped out how the gravitational field changed. And that change of the gravitational field is primarily due to a number of different things. The first, something that we need to correct for, is topography. Think about you standing next to a mountain. You have this giant mountain which represents a massive rock higher than you, i.e., it's gravitationally pulling up on you. Yes, in a much smaller way than the Earth below, but its effect is measurable and we can calculate it. So we need to correct any gravity data we gather by topography. The distance from the center of the Earth is obvious. The further you are away from an object, you're going to have a lower gravitational attraction between it. And it's pretty easy to understand. So this is just distance from the center of the Earth, or elevation, which means you need really precise GPS measurements to be able to correct for that. And lastly, the main reason why we measure gravity, especially here in this instance where we're doing Bouguer gravity, is we're looking for differences in density or the mass beneath the ground. So once the data set or measurements are corrected for topography and elevation, the resulting gravitational field, the map you create from it, shows changes in the subsurface density. In other words, a large iron deposit will have a higher gravitational field. You'll measure more gravity due to its high density directly above it. An example where you would have a lower gravitational field would be something like a salt dome, as it has a much lower density generally than the rocks around it, and therefore lower gravitational field strength over it. In this case, for the Ninole Hills, this study focuses on an anomalous feature called, as you guessed it, it's in the title, the Ninole Hills. It's a topographic high, or set of hills, on the southeast flank of Mauna Loa. It also represents the oldest exposed rocks on the edifice, dated at around 100 to 200,000 years old. Remember, we just got done explaining that 90% of the surface of the volcano is less than 4,000 years old. And these rocks are over 100,000 years old. Which really means something special needs to have happened to preserve these rocks at the Earth's surface. Otherwise, they would have been repaved over newer eruptions multiple times. There must be something special, either about the rocks themselves or some other process that's going on. So the question the study set out to answer was, what are the Ninole Hills and what caused them? Okay, now for some quick geography of the Big Island of Hawaii and Mauna Loa, so further explanations might make more contextual sense. At least that's what I'm going for. Remember, a picture is worth 1,000 words, but all I have is the power of my voice. So Mauna Loa is one of 5 volcanoes on the Big Island of Hawaii and overlaps with 3 of them. The currently active and famous Kilauea Volcano Summit is southeast of Mauna Loa's summit. Northeast of Mauna Loa's summit is Mauna Kea, and northwest is Hualalai. The one edifice, or the one volcano, that does not overlap with Mauna Loa is the heavily eroded Kohala volcano. It is in the northernmost area of the Big Island. A long way of saying that Mauna Loa is surrounded by other volcanoes, except on its southeastern flank. And that detail will become important. So Mauna Loa, like Kilauea, usually erupts from either of its rift zones or summit. There are some radial events, and those are important, and I probably shouldn't ignore them. But I will for the rest of the explanations, as radial events are historically rare. The historical record starting in 1843, Mauna Loa's had 34 eruptions, and only 2 of those have been radial vent eruptions. Okay, fine, I didn't completely ignore them. But the real stars of the show are the rift zones and the summit. Rift zones are inherently unstable, as there's movement along their axis from magma that intrudes along them. The movement of that magma is also complex. It deforms that whole rift zone in complex ways that is different than just 2 directions directly away from the axis of the rift, because you've also got deformation up, and then you have subsidence as the magma may move to somewhere else. It's a very complex, dynamic area, even though, generally speaking, the rift zones are moving apart. Now, the Ninole Hills themselves, they poke out of the southern slopes of Mauna Loa. If you're driving southward, away from the summit of Kilauea, you will see them along Highway 11 near Pohala and Punaulu Beach. I hope I'm pronouncing that second one. I know some of my colleagues from Hawaiian Volcano Observatory would be very cross with me if I had done that poorly. Just to be clear, it's not like they're superimposing and they're awe-inspiring or crazy large or anything like that. But putting it into perspective, everything else you see along the slopes of Mauna Loa, they are quite different. The slopes of Mauna Loa are a gentle, kind of constant slope. There isn't much topography there. So these things are fairly obvious. Several hypotheses have been proposed to explain how the Ninole Hills formed over the years. The first idea was that the hills were the remnants of an older summit of Mauna Loa, or perhaps a different Hawaiian volcano, Mohokea, a protovolcano. This idea has been dismissed due to the geochemical characterization of the lava flows comprising of the hills, as they show no appreciable difference with Mauna Loa lava. It's important to note that the different volcanoes in Hawaii do have somewhat of a unique chemical signature. It is thought that the mantle plume beneath the island is chemically zoned, allowing for flow identification, or i.e., which volcano produced it via chemistry. You can almost do a whodunit, which can be kind of complicated and useful when we're starting to look at flows that are intermingled, because Kilauea volcano and Mauna Loa volcano, for instance, overlap each other. So in that area of overlap, if you really wanted to figure out which flow belonged to which volcano, you can using chemistry. The other ideas require some data to distinguish them apart. The first idea that I really needed to get a handle on and kind of probe is the idea that the Ninole Hills were due to faulting and landsliding. The idea being that large blocks came from further up the volcano, leaving a topographic high. The second one is kind of a grouping of individual ideas, where several studies suggested similar hypotheses, revolving around the idea that the Ninole Hills were once the site of an active rift zone. For example, the existence of a previously unrecognized orientation of Mauna Loa's southwest rift zone, or a proto-rift zone south of Mauna Loa's summit to explain an elongated gravitational high. Third, seismic velocity models suggested the Ninole Hills may be a failed rift zone, stretching from Mauna Loa's summit through the Ninole Hills and out past the coastline. So each of the mechanisms that I've just described will leave a distinct geophysical signature due to the differences in subsurface modification. This study presents Bugge gravity results to infer the subsurface density structures and hopefully distinguish between the formational mechanisms for the origin of the Ninole Hills. So, data collection time. With the GPS and a gravimeter, I got to drive around and, where allowed to by the local landowners, hike the slopes of Mauna Loa around the Ninole Hills, pressing buttons. Slowly but surely mapping out the changing gravitational field on the slopes of Mauna Loa. It was also a privilege to be following in the footsteps of others. Remember, in science the phrase goes, standing on the shoulders of giants. Well, there was an island-wide gravity survey previously done by a past chief scientist in charge at HVO, Jim Kawanawa. This data set allowed me to remove the effect of deeper mass changes and focus on the region just beneath the Ninole Hills. The data then showed, once corrected for, an elongated density high beneath the Ninole Hills, which was, roughly speaking, parallel but clearly separate from the current location of the rift zone just to the north called Mauna Loa's southwest rift zone. The current southwest rift zone also had a density high along its axis. Large density highs in Hawaii are going to be due to magma. Not necessarily the active magma, but due to activity. As magma cools underground, crystals start to form. One of the first crystals to form is olivine. Olivine, once it's formed, is denser than the magma it formed in, so it will start to settle out towards the bottom of the magma chamber. Over time and lots of volcanic activity, more and more olivine accumulates in the bottoms of these magma chambers. And olivine, because it's so dense, it represents a significant mass of high dense material. That's why Hawaiian volcanoes and their rift zones sit above positive gravity anomalies. Okay, so back to the Ninole Hills. With the proto-volcano idea already kind of thrown out, the next easiest to show it is nearly impossible to be right is strictly faulting and landslides. If caused by faulting and landslides, you would not expect a positive gravitational anomaly directly beneath the Ninole Hills. Because, what part of landsliding would cause a significant increase in density? The high density means there must be magma, or old magma chambers must have been involved in some manner. Furthermore, other work that was done offshore shows that the southwest rift zone was active before, during, and after the rocks of the Ninole Hills were created. That part of the rift zone, which is well offshore, has been in about the same place for over 470,000 years. So it's not the summit. It's way too big to be a radial vent, so it must have been a rift zone. So what happened to it? One option is that it's a failed rift zone. Maybe Mauna Loa had 3 rift zones at one time. Well, that doesn't really fit the data. And the angle between the southwest rift zone and the proposed Ninole Hills rift zone is too small. Ideally, triple junctions, or the intersection of 3 rifts, will want to be at approximately 120 degrees, or at the very least quite close to it. Here, it would need to be between 45 and 90 degrees. Basically, the physics just don't work. So that left the southwest rift zone must have moved. Back 200,000 years ago, it must have gone through the Ninole Hills and merged with the current portion of the offshore rift zone. That is the only model that fits all the data. The geochemistry, the island-wide gravity survey, the seismic data, and importantly, my data over the Ninole Hills. But now we get to what I think is the coolest part. How and why did it move? We don't need to look too far away from Mauna Loa to find a volcanic rift zone that is moving. Kilauea's east rift zone is moving seaward slowly over time. We know this because gravity measurements. I love gravity. And topography. The southern flank of Kilauea is moving slowly due to its own weight sliding towards the sea. This is also moving the rift zone seaward. In this case, its gradual movement can be seen through gravity measurements, as the gravity or the gravitational field across the rift zone is asymmetric. This just means the shape of the map, or the shape of the profile as you go across the rift zone, is different on either side of it. The seaward side drops off much faster. Why, you may ask? Well, because there's just not been that many magma intrusions and activity seaward from the east rift zone. To rephrase this, as you approach the current rift zone from inland, or you're traveling approximately south, the gravitational field gradually increases as you pass over old axes of the rift zone of Kilauea until the rift is crossed, and then it drops off quickly as there's been no long-term volcanic activity beneath the ground there. However, we can't use Kilauea as the model, as there's no gradual buildup here beneath the Ninole Hills. It's an isolated density signal completely separated from Mauna Loa's current southwest rift zone. This means whatever happened must have happened in a geologically instantaneous way, because it left nothing behind. Therefore, it happened quickly. To be honest, this last part took me a while to arrive at. What in Mauna Loa's past could have changed the stresses in the volcano to force a rift zone to drastically change.
I glossed over something really important, and now I need to explain it. That's right, it's time for a deviation. Remember, near the beginning of the episode, I gave an abridged explanation of isostasy. The Big Island of Hawaii represents a significant amount of mass sitting on the Pacific lithosphere, and all that mass is pushing down on it. And remember, when you push down on it, you're also going to cause flexure of the crust, like the pool floaty in the pool when you're adding a human weight to it. This is also important in the sense that the volcanoes are also pushing on each other, because all that mass isn't just also trying to go down, it's trying to go out. So I just explained that Kilauea's east rift zone is moving seaward, and it's because that flank, that gravitational mass of that flank of Kilauea, is moving seaward under its own mass. It's created its own fault zones. It's sliding due to gravitational instability. It's really important to be able to think of these large volcanoes at bigger scale, with their own stresses and strains. Another thing we also have to remember, though, is that these volcanoes are built through eruptions, and eruptions, especially when they hit water, they tend to form just broken bits of rock. In other words, the edifice, or the volcanoes, the big mountains that make up the Big Island Hawaii, aren't exactly just full of coherent rock. They're full of void space, they're full of broken bits, they're just full of faults and deformation, and all the like. And I've already alluded to all this, but just to bring it home, these volcanoes represent high places, and high places like mountains tend to fall down. And this does happen periodically at ocean island volcanoes around the world, and we see evidence of this for the Hawaiian volcanoes themselves. Very large mass wasting events. Mass wasting just means a very large landslide or debris flow causing significant amount of mass to slough off of the edifice or the volcano. And we have seen this historically at Kilauea, where we have new eruptions entering the sea. They build out these lava benches, and they can collapse. Although this is on a much smaller scale. Okay, so now to end the deviation and looking back at trying to figure out what kind of events created the Ninole Hills.
The first event I investigated was Kilauea. Hawaiian volcanoes start small and eventually grow. At one point, Kilauea wasn't right up against Mauna Loa. Mauna Loa wasn't buttressed by Kilauea. The masses of the two volcanoes did eventually start to interact. And this interaction or buttressing of the south flank of Mauna Loa definitely would have changed things. But I can't really come up with a mechanism to explain the data and cause the rift zone to move in the way it would have to. Although, I also can't rule it out, because Kilauea growing up to the point where it would start to affect Mauna Loa's southern flank definitely would have changed things. The second idea, and the one that fits the data the best, is landslides and debris flows. At the time this paper came out, this was not yet recognized for Hawaiian volcanoes. However, that's not the case at other island volcanoes. For example, Engaya volcano, Tenerife, Canary Islands, where a geologically instantaneous reorganization of rift zones has been suggested due to large mass wasting event. Using geological dating and careful geological observation, it was suggested that Engaya volcano originally had straight east-west rift zones. A large landslide occurred on the northern flank of the volcano, which caused the rift zone to bend as it conformed to the landslide's scarp. The idea here is the landslide unloaded enough mass from the volcano, changing the stress regime of the edifice. It was easier for the magma to intrude through the landslide scarp than go up significantly more material to reach the old rift zone axis. The issue for this direct tie, and the reason it probably wasn't made before this paper, is back to the fact that Mauna Loa is so active that it repaves everything. Engara had much more dissection, much more erosion, much more availability of material to date and put pieces together. But I've gotten ahead of myself. Mauna Loa has had some crazy large landslides and debris flows. Mass wasting, such as the Alaka, and I'm probably pronouncing them, debris flows, both 1 and 2 on the west flank of Mauna Loa, has together transported 200 to 600 cubic kilometers of material, and has been dated to 200 to 240,000 years and 127,000 years, respectively. So that's the two different debris flows. The removal of just one of these debris flows of 100 cubic kilometers of material, which is a crazy amount, would have changed the stress regime and the strain on Mauna Loa and potentially caused its southwest rift zone to jump northward or migrate fast enough not to leave large magma chambers, and therefore no density signal for me to measure. I think I'll just read the conclusion from the paper, as it isn't full of jargon and says it pretty much perfectly, in my opinion, or at least perfectly from my perspective. Geologically fast rift zone migration or orientation change can also explain the preservation of the Ninole Hills, as a stable rift zone will create a topographic high along its axis. When the rift zone moves, the old axis will shelter land seaward from lava inundation. Although it is not possible to conclusively determine the mechanism responsible for the image density anomaly beneath the Ninole Hills, we interpret the gravity data as evidence of an early Mauna Loa southwest rift zone orientation. This study suggests the migration or offsetting of rift zones by large landslides is likely more important to the development and modification of basaltic island volcanism than previously recognized. There, that's the end of the conclusion. And quite frankly, it just goes to show, no matter which volcano you prefer, don't get too attached. They all have their faults, and then they just fall down. So, hit subscribe, tell a friend, leave a rating, and if you're able to, you can also join the Patreon, or just drop me a line on any of my social media. See you again in 2 weeks' time.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us sex always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear it? It's echoing through your bones. In this melodic maze we